So, good morning, everyone. As you can probably see from the pictures, I am not Birte Forsman, unfortunately, because she couldn't come, and because of this young fellow who decided, whoops, sorry. It's going to take me a moment. The mouse, yeah. Okay, well, so our son just had a nice tooth first coming, and so she had to stay with him. So let's start with a little quiz. How many structures in the subcortex? So thankfully I didn't go all the way to the answer, but how much would you say? 10? No, that's too small. Maybe 50? Yes? No? 400, that's a lot, isn't it? Right? Well, yes. So you already know the answers. We're around 450. Let's try again. So 455. Okay. Okay. All right. So 455 according to the Federative Community on Anatomical Terminology, which is about twice the number that has been mapped in the cortex with the latest techniques, as well as very classical anatomy. So how many of them have been mapped with MRI? You probably know also as well. 7%. So that's not a lot, right? In fact, if I can get to this slide, if we were to consider that the map of the world would represent the subcortex, the part in red would be what has been mapped, and we would already be in the dark areas of terra incognita. So why is that? Why are we not mapping all of this? We are mapping the human brain. That's what this meeting is about. What is it about these nuclei? Well, the first thing, it's quite obvious from the pictures already, they're small. So it's pretty hard to see them even with advanced methods. The second part that I will hopefully get to at some point is that they also really like each other and they just stay nice and cozy together. So they're really, really tightly packed, and worse than this, they're as far as they can from the cortical surface, being nicely protected in the middle of the brain and really far away from MRI coils. And just to make things worse, because they also have some complex composition, including iron and neuromelanin, which changes quite drastically their response to MRI signal. And all of this, of course, is very important, as we saw already, because of the clinical applications for deep brain stimulation, which is a very promising and increasingly popular treatment for movement disorders such as Parkinson's disease, but also for a wider variety of neural disorders that are looking for new targets also in that area. So it is really important now to know two things: where we are in the subcortex and what those nuclei also are doing. So in this talk, I will focus on the subthalamic nucleus and its structural and functional subdivision. First, looking at the structure with postmortem brains, and then in vivo with fMRI, looking at the function. And then we'll have a bit of an outlook. So have a three subdivision in the STM. So we saw just now that there's definitely a lot of different projections that go more on the motivational, cognitive, or motor side of the cortex. And so we have to try to figure out where we are when we want to implant electrodes. So we can just image it with MRI. So if you are working in a clinical scanning place, you will have a very nice 1.5 Tesla scan, maybe. Whoops. If you're lucky, that will not be very efficient to see data. You will see mostly noise. I apologize for this. Very not okay. Never mind. All right. No, I want to go the other way. All right. Well. So without the slides that we saw in a very fast fashion, so you could maybe appreciate the difference between 3 Tesla, well, 1.5 Tesla where you just see noise, 3 Tesla where you start seeing some structure, but you have to squint a lot, and then 7 Tesla where everything is very nice and sharp. However, still not as good as you could get with ex vivo samples, which have the nice properties of not moving for a large amount of time. So in order to study that more in detail with MRI and microscopy, we embarked in a quite challenging journey to bring post-mortem brains from human donors all the way from MRI with high-resolution post-mortem imaging of structure and diffusion to then block face imaging and histology in this side. And with one of the very tricky parts in this type of endeavor, which is to really make the spatial link between the 3D brain that has been imaged with the MRI and the slices that we obtained with histology. And that was nicely presented by Anneke Alkemade in a poster on Tuesday. From this video that will or will not show something great, you can also appreciate the quality of our work in obtaining beautiful block face images. So all these are obtained by cutting very carefully the brain at 200 microns over the space of 2 to 3 days, and obtaining very, very carefully aligned sections, which allowed us to reconstruct that 3D brain that I just showed. The last step then afterwards is staining, and there we also have the challenge to put together the free-floating stained slice images back to the block face image. However, because it's a 2D to 2D problem, we hope to be able to solve it with a lot more precision than is usually done. But going back to the STM, we have started a little more simply and just took a small block to work with. And then we did the same type of procedure, cutting into many slices, this time with much finer resolution, with paraffin embedding, and then staining with a lot of different immunohistochemistry stains to try to reveal the richness of its composition. So you can see the type of stains we obtained on the left with the different slices, and then on the right we have a reconstruction in the other axis with the slices that have been obtained from the same stain with about 300 microns apart. So with that, we try to look for subdivisions. So are we in a completely homogeneous structure? Do we have mixtures that are overlapping? Or do we have sharp borders that really indicate that we have not maybe 455, but 458 structures? Well, from these results, you can appreciate that there is variability in the different stains. There are some borders that could be seen in some of the stains, but you can see that even though there is heterogeneity, there is no consensus on those boundaries in any of the stains. So it looks like there is a lot of variability in the composition of the STN. However, we cannot really see any sharp borders that is systematically there. So we go with the second model, looking more at mixture of gradients of overlapping composition. Now I want to go briefly to the in vivo case. There we had to do a little bit of optimization. I mentioned that subcortical structures were often rich in iron. It is a case of the STN. So if you take a classical MRI fMRI imaging technique, by the time you're trying to get some bold response, all the signal is gone from the STN, and you just get noise. So we tried a few different protocols with shorter echo times and high resolution needed to get to the STN. We did that within a stop signal task in order to get proper responses that we knew would happen in the STN as well, and looked at things like TSNR and the response to the task to look at which type of protocol would be best. The TSNR showing that because of its slightly coarser resolution, the protocol with 1.5 isotropic voxels but a very short TE of 14 milliseconds was the most optimal. Since then, we've expanded those results to look also at multi-echo fMRI, which was presented on Wednesday by Stephen Militic. Then we looked at the functional subdivisions with a slightly different task. But first, we created artificial subdivision of the STN by looking at the main axis and then creating 3 zones of the equal size that would be dorsolateral, central, and ventromedial in locations. So that resulted in about 5.5 voxel in average in all the subjects, and we used that 70 optimized sequence. We took a random dot moving task with a cue. So the people were presented a cue that was coherent or incoherent with the subsequent motion, and then you would have random dots coming, and they would have to choose which direction they were from. And to look at the different components of the function, we looked at different manipulations with a payoff, changing difficulty, and changing the hand for the response. We fitted the behavior with the hierarchical diffusion drift model in order to check that the behavior was corresponding to what we expected. Here we showed the model and the corresponding reaction time quantiles that were obtained in the data, which show a broad agreement, even though there's not a perfect fit due to the short number of trials in the fMRI. And then we looked at how this would then map into the bold response. And there you could see that whether on the left or the right STN, wherever you look, there is not a lot of difference due to the manipulations between the between the payoffs or the difficulty and the size. However, you could notice also on the side here that, well, there might be something, but what is very clear is, apart from seeing that there is signal change, we also have a lot of noise, and we're definitely underpowered. So in conclusions, with ultra-high resolution MRI, we can look at the small subcortical nuclei, finally. With postmortem anatomy, we were able to find that the STN has heterogeneity but no sharp internal borders. and that functional MRI can show some involvement at current resolutions with optimized sequences, but that we need a higher powered approach in order to get there, for which we are currently developing a 100 subject database with structure and function over the lifespan, where we will be able to hopefully replicate this study with wider, with finer results. Sorry. Lastly, if the slide comes up, I would like to thank Gilles de Hollander, whose work this was a majority of, and of course our lab for everything else, and you for your attention and your patience with the slides.
That was a great talk.